Quite a wordy question. Question 21. Helium is the second most abundant element in the universe. Most common isotope of helium is 4,2 helium, and the nucleus of this isotope has a rest energy of 3,728 MeV. Make a note of that. 3728 MeV. If you don't know what a mega electron volt is, it's a unit of energy. These individual particles have very small amounts of energy, so we don't want to use joules too often because we'd have ridiculously big numbers. Let me give you some more text. In 2011 at the Relativistic Heavy Ion Collider, antihelium nuclei were produced. Nuclei of antihelium are made up of antiprotons and antineutrons. It is suggested that an antineutron can decay to form an antiproton in a process similar to beta minus decay. And in one particular collision between an antihelium nucleus and a helium nucleus, the nuclei are annihilated and 2 photons are formed. And after all that, all they want to know is what an isotope is. So that's easy enough. Same proton number, different neutron number. You'll notice this has come up a lot, so make sure you know this. Very common question. Right, B. Explain why the 2 photons are formed instead of a single photon when a helium nucleus annihilates with an antihelium nucleus. So if we've got 2 helium nuclei travelling like this, they're going to annihilate each other, they're going to collide with each other. Think about what properties have to be conserved in any interaction, and one that springs to mind is momentum. Momentum is conserved. Now, if these were to produce just 1 photon, then momentum wouldn't be conserved. And you might argue that, well, photons have 0 mass, so they don't have momentum, but in fact they do. And momentum means something slightly different in this context. So the only way we can conserve momentum is if we have 2 photons, one going that way and one coming this way in opposite directions. So momentum before is equal to do that, and momentum after is also equal to 0, because the 2 photons momentum is going to cancel everything out. Right, part C. So using data from the passage, the maximum frequency of the photons produced in this annihilation, calculate the maximum frequency produced in this annihilation. Right, so to calculate the frequency of a photon, it's E equals hf. F is the frequency, h is Planck's constant, and E is the energy, but it's the energy in joules, so we need to remember that. So to work out the maximum energy, before from these 2 nuclei, the normal one and the anti one, we first of all need to work out 2 times this number. Now that is in mega electron volts, so that gives us 7456 MeV. That's because there's 2 of them colliding. What I now need to do is really sort of convert that into joules. It's going to produce 2 photons, so we'll have to halve this number as well, which might seem a bit counterintuitive because you've already done 2 times there. Why are we dividing it by 2? But it's a simple case of that's basically what the mark scheme requires you to do to show that you understand it. So our frequency of our emitted photon from this equation would be E over h, but we need E in standard units. So to convert between mega electron volts and joules, you need to multiply by 1.6 times 10 to the minus 19. That's pretty much the definition of an electron volt. So we're going to do that first. 7456 times 1.6 times 10 to the power minus 19. That gives us, don't forget that, should be times 10 to the 6 because it's mega. That's going to give us 1.193 times 10 to the power minus 9 joules. You should be getting a small number for this, Remember, a joule is quite a big lump of energy for a particle. It's small for us, but it's a massive chunk for a particle, so that seems to be about right. Then we can go back into this equation. There's 2 photons produced, so 1.193 times 10 to the power minus 9. First thing I need to do is divide all that by 2, and then divide our answer by Planck's constant, 6.63 times 10 to the, minus 34. And that will give us an answer in hertz, 8.99 times 10 to the 23 hertz. So that's quite a high frequency photon. That's certainly in the gamma sort of region, I suspect. Right, I think there's more. Yep, there is, so let's make some room. Part D. Complete this equation for the possible decay of an antineutron. So let's copy this out first. We've got an antineutron which is going into an antiproton by the looks of it, plus something else. And it does say in the question earlier on that it undergoes a manner similar to beta decay. So let's look at quantum numbers first of all. Baryon number on this side is an antineutron, so it has a baryon number of -1. While that has a baryon number, an antiproton has a baryon number of -1 too. So the baryon number for the other 2 particles could be 0. I suppose it could be +1 and -1, but they're going to be 0. The charge on this particle, an antineutron has 0 charge, an antiproton has a negative charge, so that's going to be -1. So I'm going to need something which is going to have a positive charge here and possibly a 0 charge there. Lepton number is another quantum number that's conserved. We have no leptons in the antineutron and we have no leptons in the antiproton, but I'll leave these blank for the minute. So to conserve charge, we need something with a +1 charge. That's likely to be a electron. Put a little positive sign to make sure it's a positively charged electron. Then the charge over here will cancel itself out. So that means we've now got a -1 as a lepton number, so I need something with a +1 to counteract that. So something with +1 lepton number, looking at these numbers now, I want 0 charge and it can't be a baryon, so the only reasonable suggestion would be a regular neutrino. And finally, what interaction would be responsible for the decay? Well, it looks like charge has been transferred from one to the other, so that's going to rule out electromagnetic and gravitational. It's going to pretty much just leave the weak nuclear force because that's the only one that can transfer charge. So I would go with weak nuclear for that one. Right, finished.